Let's continue with notes from slope fields. So this is the second page here, back page. Determine the differential equation being graphed by each of the slope fields below. Then sketch a solution that passes through the indicated point. So on the previous page, for notes, we only plotted 8 points on the slope field. So we were not really able to see the shape of the graph, but now this slope field is completely filled in. Each of these short line segments represent the slope at each of the ordered pairs for for one of these respective differential equation. So one thing that we can do is to help narrow down our choices is we can look at some common patterns. So if we look at the slopes for each of these short line segments, we're going to see that most of them are going to be positive slopes. In fact, they're all positive slopes except for what you see on the y-axis. Right? These are where slope is 0. But everywhere else, we're going to see varying degrees of positive slope, either really steep or we see that these line segments get less and less steep, and then it's going to start increasing in towards the positive slope as well. And we can also look at places where slope is 0, so that can help us narrow down our choices. So we see that anywhere where the y-axis or where x is equal to 0, we're going to expect a slope of 0. Okay. Other things that we can do is look at the slopes along the x-axis. Notice where the slopes are positive and notice where they're negative. So we see that we don't see any negative slopes here. So that means we should be able to use that information to help us narrow down which one is going to work and which one is not. So if we look at part A here, we could have some negative values, right? If I choose negative 2, 1, negative 2 cubed would be negative 8. So, but that we know that's not true because we see positive slope in this region. So we know this can't be the correct slope field. Well, this can't be the correct equation for this slope field. Let's go down to C. We can't have any negative slopes based off of the slope field, but if we choose some negative x values, we may get some negative slope, so we know this can't be the correct differential equation either. Here, we see y in the denominator, so if y is equal to 0, meaning anywhere on the x-axis, there should not be any line segments because we know slope cannot exist where we have a 0 in the denominator, or the value cannot exist where there's a 0 in the denominator. But we see that's not going to be true here because we see values, we see certain line segments on the x-axis. And for part E, natural log of x, we know x can't be negative value because if x is a negative value, we know that the natural log is not going to exist. But we obviously are seeing some negative values, negative x values, that's producing a specific slope. So we know that ln of x can't be the correct one either. Okay, which brings us to part B, right? The reason why we're getting positive slopes everywhere except for where x is equal to 0 is because we see that x is squared. So any negative x value that is being plugged in will produce a positive value. And it also makes sense that anywhere on the y-axis where x is equal to 0, we're expecting that the slope is going to be 0 as well. Plug in 0 for x, we get 3 times 0 squared. So these differential equations can help us identify each of these individual slope segments, which is used to create the slope field. But let's go ahead and take this a little bit further. I want to show you what happens if we solve this differential equation. So let's solve this differential equation. So we have y over dx equals 3x squared. We're going to separate variables, move the dx over to the right side. So we have integral of dy is equal to integral of 3x squared dx. We take the integral of both sides. Integral of 1 will simply give us y. Integral of 3x squared will give us 3x cubed over 3 plus c. So our resulting general equation is y is equal to x cubed plus c. Now let's consider what the shape of this graph is. X cubed plus c, cubic function, we know is going to have a general shape of a curve that is always increasing, that's positive slope everywhere except in this case at 0, 0. And this plus c is just going to be a vertical translation, so a vertical shift. So maybe if it's plus 3, then the graph will be up here. If it's minus 1, then the graph will be down here. Now, if you look at this shape of this general equation and take a step back and look at the shape that is created from these line segments, you're going to see similarities, right? If you follow this graph from left to right, you're seeing that if you connect these points and follow the flow of this graph, that it's going to resemble this family of function, this x cubed plus c. So that's one thing that you can do to help you differentiate between these two forms. So if it is in differential function, then these ordered pairs will match the slope of each of these individual segments. However, if you're looking at the general solution, then you're looking at the flow of the graph and the shape of this graph. So this next part says sketch a graph that passes through the indicated point. So if we just follow the flow of this graph and we're going to go through that point, we see that we have a graph that resembles a particular particular x cubed graph. Okay. All right, so the shape of the slope field graph resembles the family of functions for the general solution above x cubed plus c. Okay, let's look at number 3. So we see, if we look at this graph here, we see a couple of things that we don't see anything on the x-axis. We don't see anything on the y-axis either. However, it could be that there could be something here. Maybe there's a slope of 0 here, and it's just being hidden by the x-intercept, by the x-axis. However, the y-axis, we know there's definitely not anything here because we can't have vertical lines that represent slope, because then that would be undefined. So we know this means that at least there must be an equation where the slope is undefined on the y-axis. So basically, we're looking for where x is equal to 0, where there is an x in the denominator. Okay. And we can narrow down our choice just by looking at the possibilities here. So dy over dx equals x minus 2 equals x cubed equals x minus y. None of these will produce values that will where if I plug 0 in for x, I'm not going to get undefined here. Okay, and same with part E. I should get positive slopes for anywhere on the graph, but I'm seeing some negative slopes here. I'm seeing some negative slopes here. So that's going to bring us to part D. Right? There's an x in the denominator, and by looking at the characteristic of this graph, this matches because the y-axis ordered pair are undefined, and the x-axis has a slope of 0. And so we expect that from this graph. So the answer choice is D. Okay. Let's take this a step further and solve this equation so that we can match the solution with this overall shape of this graph that's produced from the slope field. So we're going to solve this differential equation. Let's separate the variables. So bring the y to the left, bring the dx to the right. So these are both in the form of the integral of 1 over u, and the integral will simply be natural log of u. So natural log of absolute value of y is equal to, on the right side, natural log of the absolute value of x plus c. We want to solve for y, so we want to get the y out of the natural log function, so we exponentiate both sides, and we get y is equal to e to the natural log of x times e to the c. This will produce x, but here this is a constant, so we can pull the constant in front, so we're simply left with y is equal to cx. Now y equals to cx is a linear function, and this makes sense because the slope field does resemble a linear function, with various forms of linear functions with various slopes. So we see a line here, we see a line here. However, we want to sketch a solution that passes through this indicated point. So we can just follow the flow of this graph. And at 0, it's going to be undefined for this specific differential equation. So we're going to the graph has to stop here. Okay, but it will continue in the negative direction. So we indicate that with an arrow. Okay, let's look at number 4 here. Sketch the slope field for the following differential equation, then find the general solution analytically. So dy over dx equals negative x over y. I went ahead and I found all the ordered pairs and found the slopes and drew these line segments representing the slope. And as you can see, I left the x-axis completely empty because when y is equal to 0, dy over dx, the slope will be undefined. Okay. So now let's find the solution. So separate the variables. Y is on the left, x is on the right. Take the integral of both sides. We get y squared over 2 is equal to negative x squared over 2 plus c. I'm going to multiply everything through by 2, and I'm left with negative x squared plus 2c. Take the square root of both sides, and I get y is equal to plus or minus square root of negative x squared plus c. Now, if you plug this in your calculator, or you can plug in any value for c, you're going to get either a graph that's going to resemble a semicircle above the x-axis or a semicircle that is below, opening up. And the general solution should match the shape of the slope field, and it does, right? If we look at the graph, we see various, if we follow the flow of this graph, we see various forms of plus or minus negative x squared plus c.